Section 9.9 is about representations with power series. So now that we've dealt in 9.8 with convergence of power series, now what we're going to do is try to write a function which is not a power series as a power series. And in this section, the main tool that we're going to use is that convergence of the geometric series once again. If you recall, what we said way back in section 9.2 was that if we have a sum of a series which look like a times r to the n from n equals 0 to infinity, then that thing will add up to a over 1 minus r when r is between -1 and 1. So these two things are the same when r is between -1 and 1. So what our goal is going to be is to write a function in a way that looks like a over 1 minus r. And if we can do that, then that function can be written as a power series a times r to the n. Now, r, just like we saw in 9.8, is going to be something like x or x minus 2. It's going to have some value of x associated with it. And a is going to be, we're going to force a to be a constant this time. So again, we replace that little r with an expression that concerns x, and we'll center it at whatever we want it to be centered at, basically. And then we'll go backwards. We'll say our function can be written as something that looks like this, and we'll go backwards and get the infinite series or the power series based on this equivalency when r is between -1 and 1. All right. By the way, r here, replacing r with x minus c, that's what we're always going to do. So we're always going to be looking for x minus c there. All right, so let's take a look at this example. Let's say we have the following function. And now I've created this function so it's really easy to deal with. As we get later and later on in this section, the functions get a little bit more complicated, more difficult to deal with. So let's look at this function. F of x equals 1 divided by 1 plus x. We're going to center this geometric series we want to center a geometric power series at 0. And we want that geometric power series to be equivalent to this function. So how are we going to do that? So the easy way to do this is to take 1 over 1 plus x. And remember, we want our function to be looking like a over 1 minus r. So the only thing we have to do is basically make this plus into a minus. And we're already centered at 0 because we have x by itself. X by itself is the same thing as x minus 0. So we already have x by itself, so we're already centered at 0. All we have to do is change this plus to a minus. The easy way to do that is to take minus a negative. So a plus is minusing a negative. And so now we have our function, which looks like a over 1 minus r. And in our case, the a happens to be a 1, and the r happens to be a negative x. Now you can write this in other ways if you'd like, but that's the basic premise. We make things look like a over 1 minus r, and so this function will be equal to the power series whenever the r, again in this case that's negative x, is between -1 and 1. So basically, by the way, if you multiply all three sides by a negative, you have to switch the side. So basically, when x is between 1 and -1, this function and this power series are the exact same thing. All right? So this section is really a test of whether we can algebraically manipulate our function to look like a over 1 minus r, where r is centered at the right place. Now, this gets more and more difficult as we get going. So one trick that we used in the last was changing the plus to a minus. That's pretty straightforward. Well, what if we don't have 1 over 1 minus r? What if we have something like 1 over 9 minus something? So let's find a geometric power series for this function, and we're going to center that geometric power series at 0. So 1 over 9 minus x, how are we going to deal with that? Well, quite simply, we take a look at 1 over 9 minus x. We already have this centered at 0. A lot of times I like to put parentheses around the x once I've centered it at the right place. So we've already centered this at 0, but we need 1 over 1 minus r instead of 1 over 9 minus r. So the way to do that is to multiply top and bottom by a ninth. Now, if you multiply the top and the bottom of any fraction by 1/9, that doesn't actually change the value of the fraction because we're multiplying by 1. Obviously, I picked 1/9 because that 1/9 times 9 is going to give me a 1. In the numerator, I get 1/9. In the denominator, I have minus x over 9. Now, by the way, this is still centered at 0 because I can still write x minus 0 right there. And that is my 1, excuse me, not 1, a over 1 minus r that I'm looking for. So dividing by a number or multiplying by a coefficient or dividing by some coefficient actually doesn't change the place that we're centered at. So 1/9 over 1 minus x over 9 is my a over 1 minus r. All right, so all we have to do is, now that we've established that, now my function can be written as, well, if a is 1/9, we write that. My r is x over 9. We write that. So my function is exactly this infinite power series, or I should say this power series, whenever the r, again in this case that's x over 9, is between -1 and 1. So this function is equal to this power series for any value of x between -9 and 9. All right? So anywhere where this converges, it's going to be equal to the function. And then we can utilize all the stuff we know about power series as we like for this f of x. So what have we dealt with so far? We've dealt with a couple of things. First off, we dealt with changing this plus to a minus. Then we said, well, what if we don't have 1 minus r on the bottom? What if we have 9 minus r? We've dealt with that. Now we know how to deal with that. And the last step is to say, well, what if we wanted to center this at something other than 0? So let's take the exact same function, and let's say we want to center it at a number like 4. So what we're going to do, is we're going to want to center this at 4. I'm going to show you how to do that. here we go. So the first thing I do is I write the function 1 over 9 minus x. And then I say I want to center this at 4. So what I want to do is instead of having x here, I'm going to replace that with an x minus 4. Now that actually changed, if I were to just replace the x with an x minus 4, that would change the value of that denominator. So I want to keep the value of this denominator the same. Notice that there's a minus sign out here. If I were to distribute this in, what really happened is I added 4 to the denominator. So in order to undo that, in order to balance things out, I'm going to subtract 4 in the denominator. Hopefully that makes sense. This plus 4 is coming from distributing the minus into the x and the minus here. In other words, if I would have distributed that minus, I would have gotten minus x plus 4. Notice we've changed the denominator by a factor of adding 4. Now I want to cancel that out, so I do a minus 4. So essentially I'm adding 4 and subtracting 4 to the denominator in a unique way. And so what that's going to do to my denominator, 9 minus 4 gives me a 5. And then I'm going to do 5 minus x minus 4. So there you go. Now we have a function that's centered at the right place. Obviously, this is centered at the right place, but I do not have a over 1 minus r. So I have to go back and do that same trick we did in the last problem of turning this 5 into a 1. If you remember, so here we have 1 over 5 minus x minus 4. The trick was multiply the top and the bottom of the fraction by 1/5. Well, 1/5 in this case. In the previous case, it was 1/9. But since we have a 5 here, in order to turn that into a 1, multiply by 1/5. So you get 1/5 divided by 1 minus, well, we're going to get x minus 4 over 5 when you multiply 1/5 times x minus 4. By the way, x minus 4 over 5 is still centering this at 4. So that's perfectly all right. So what we're saying is now we have a function that looks like a over 1 minus r. Although my a and my r are a little bit cumbersome, that's still just a over 1 minus r. So we can write it as this infinite sum, again, starting at 0, going to infinity. A is 1/5, and r is x minus 4 over 5. And there you go. And so my function that I started with, 1 over 9 minus x, is actually going to be equal to this power series when r is between -1 and 1. In my case, r obviously is x minus 4 over 5. That means, well, when you multiply by 5 on all three sides, you get that, add 4 to every side. You figure out that this power series is equal to the function whenever x is between -1 and 9. So that's how we can center at almost any value we want. Now I said almost any. There is a value of this function, 1 over 9 minus x, that I cannot center at. And that value is 9. Okay? If you did this process with 9, it turns out you can never get a 1 because this bottom, you can never plug in 9 for x and get your function to be meaningful. In other words, if you were to graph this, let's go ahead and graph this. So here that function is graphed. you can see what's going on here is we're getting an asymptote at the value where x is equal to 9. So x equals 9 is an asymptote of this function. So we can't center it at this function because at that point the values of the function go off to infinity. But we can center it at any other number other than where we get 0 in the denominator. By the way, that was also true for our previous problems. So this function we can center anywhere other than -1 because when you plug in a -1, you get 0 in the denominator. So here's what I'd like you to do. I would like you to push pause on the video and try to use those 3 techniques that we just did to find a geometric power series for the following function and center that geometric power series at 6. All right, hopefully you went ahead and did that and ended up with something like I did here. So if we want to center the function at 6, we're going to replace an x with an x minus 6. That's going to require me to balance out the denominator. By the way, notice that this replacing the x with an x minus 6, that's a minus 6 that I've applied to the denominator. So to undo the minus 6, I have to add 6. In other words, what I'm trying to say is this coefficient of x is positive. In the previous problem, the coefficient of x was negative. So we have to deal with distributing here. So in order to undo a minus 6, we have to add 6. Now I'm going to write this as close to a over 1 minus r as I can. Right now, it's going to be 18 over 6 plus x minus 6. In other words, since I know that the r is going to involve this x minus 6, I'm going to put it in the back part of the denominator. So that's our first thing. Center it at 6. That's how we do that. The next thing is to get this 6 to be a 1. So we're going to multiply on top and bottom by 1/6. 18 times 1/6 is 3. The denominator times 1/6 is going to be 1 plus x minus 6 over 6. Now we have a plus sign here. So we can get rid of that plus sign, make it a minus sign by doing a plus is the same as subtracting a negative. So we just have to distribute a negative sign into our fraction here. Now I chose to distribute it into the denominator of the fraction. If you wanted to distribute into the numerator, you could have done negative x plus 6 into the numerator if you'd like. I tend to do it in the denominator just for my purposes. Sometimes the book does the distribution into the numerator though. Just FYI, they do it into the numerator more than the denominator. So there you go. Now I have my a over 1 minus r form that I'm looking for. A in this case obviously is 3. The r in this case is x minus 6 over negative 6. So this function can be written as a power series 3 summation of 3 times x minus 6 over negative 6 to the nth power. Again, that's whenever this r here is between -1 and 1. I'm not going to go ahead and look at where x has to be. I believe that means that x has to be between 12 and, oh goodness, -18, something like that. I don't know. Let me look at that. Never mind. I mean 12 and 0. So basically, if you go through the whole thing, you'll find out that x has to be between 12 and 0. By the way, notice that, again, this would have been fine to center at any place other than 0 because 0 is where the asymptote is. It's where the denominator is 0 when x is 0. All right? So there you go. That's how we can write a function as a power series. At least it's the same as this power series on this interval of convergence. So I want you to do one more. Try this on your own. I want you to take that same function and try to center this function at -3. So write a power series centered at -3 that is equivalent to this function around there. Push pause on the video and try that. All right, here's the solution. So if you are going to center at -3, then instead of replacing x, if you're going to center at -3, then you're going to replace x with an x plus 3. Now, we added 3 to the denominator of the function in order to do that. So to undo that, we have to subtract 3. So we're going to get 18 over -3 plus quantity x plus 3 in quantity. Now, because we have a -3 here, we're going to multiply by 1 over -3. Whoops, I apologize. So we're going to multiply by 1 over -3 in both the numerator and the denominator. Again, we're using -3, so that undoes this and makes that a 1. So 18 times 1 over -3 gives you a -6. -3 times 1 over -3 gives you a positive 1. And if I take x plus 3 times 1 over -3, I get x plus 3 over -3. And obviously this negative sign here in the denominator is really handy because when we're doing adding and then we have a negative sign in the denominator here, I can just pull that negative sign out and make that a 1 minus quantity x plus 3 over 3. So what's that mean our function is? Well, now we have the form we want. Now we have that a over 1 minus r. A is -6. R is x plus 3 over 3. So our function is equal to this power series when our r is between -1 and 1. And if I can do that in my head, that's when x plus 3 is between -3 and 3. So subtract 3 from both sides. We get -6 and 0. So this function is equivalent to this power series whenever x is between -6 and 0. By the way, notice this is always going to happen, that this power series is going to converge. One of the endpoints of the power series is where I have the asymptote of the function. So it's what makes my denominator 0. So notice that this one went from -6 up to 0. We had to stop at 0 because our function, goes off to infinity there. Obviously, that's not this function, but there we go. Let me rescale this thing. So that's what's going on, right? So we can converge anywhere up to 0, but 0 has this asymptote at x, or excuse me, we have this asymptote at x equals 0. And in our last problem, that happened as well. That always happens, that one of the endpoints of your interval of convergence of this power series will be where the asymptote is. Okay. If I have functions like this, if I have functions that I can write as a over 1 minus r. All right. Now, when I don't have just x by itself, but when I have something like 2x in the denominator, then it's going to work the same, but I have to be really careful about how I add and subtract to even out to get in that denominator step. All right, when I center this at, for instance, 6. So if you want, try to push pause on the video or push pause on the video and try to find the geometric power series for this function centered at 6. Okay, so I take my function here, which is 2 over 2x plus 3, all right? And I want to center this at 6, so I'm going to replace the x with an x minus 6. Now notice that when I do that, I have to put in parentheses the x minus 6, and outside of that parentheses, I still have this number 2. So how much did I add or subtract to the denominator by doing that? Well, if you think about it, I subtracted 12 from the denominator because 2 times x is my 2x, and then 2 times a negative 6 is a minus 12 if you'd multiply that out. So in other words, if you distribute this out, you'd get 2x minus 12. And so what I did is I really subtracted 12 from the denominator. In order to even out the subtracting 12 from the denominator, I'm going to have to add 12 to the denominator. All right. So when I have a coefficient, I just have to realize that that coefficient has to distribute, just like the negative sign distributed in one of our first examples. Now 3 plus 12, combine those, that's 15. So if you wanted to do a over 1 minus r, we're going to write this as 2 over 15 plus 2 times x minus 6. Some people multiply that out and put it in parentheses. I like to, just keep it the way it is. So now we have to get rid of this 15. The way we get rid of that 15 and make it a 1 is we multiply the top, the numerator, and the denominator by 1 over 15. I didn't write that down, but you can imagine 2 times 1 over 15 gives you 2 over 15. 15 times 1 over 15 gives you 1. And then this thing times 1 over 15 gives you that same thing, just divided by 15 now. Now we have a plus sign. The way to do this plus sign is to do a minus minus. So 1 minus, and then distribute that minus inside there. Oops, I wrote 3 on the top for some reason. I don't know why I did that. Should be 2 over 15 on the top. So we get 2/15 divided by 1 minus this big mess in here. All right. So that is my a over 1 minus r. Oops. So that's my a over 1 minus r. A is 2/15, r is 2 times the quantity x minus 6, all divided by negative 15. So when I'm trying to write my function, again, it's a messy numbers, but the concept's not too crazy. 2/15, the r is 2, whoops, let me just erase that, times x minus 6 divided by negative 15. Again, you can write that in other ways too. You can put the negative in the numerator rather than the denominator. So all that kind of stuff. And that's going to be this same function for whenever r is between -1 and 1. And you could calculate that out, what that means for x. I don't think I'll do that right now. So hopefully this makes sense. This is probably the most difficult concept in here, this distributing, get there. But notice in all of the problems, we kind of take it step by step. We always want to center first. So center at the right place first. Get something over, a number plus something centered at the right place. Make this number, which in our case was a 15, make it a 1 by multiplying 1 over 15 times 1 over 15. Once we make that a 1, then it's a matter of if this is a minus sign, we already have a over 1 minus r. If this is a plus sign, then we do change it to a minus a negative. So distribute that negative sign. Again, there's a number of different ways you could see this. You could rewrite this, but that's what it is. All right. Now, there's some other algebraic things that we can do as well. Here we had 2x. Well, what if we have a geometric power series and we're involving an x squared in the denominator? Now, depending on where we want to center this might be really easy. The easiest way to deal with this function here is to do 2 over 1 minus x squared. Well, that looks already like a over 1 minus r. And the x squared is already centered at 0 because it's like x minus 0 squared. So that's the easiest way. Just let r be x squared this time instead of letting r be x or x minus 2 or something like that. So let's go ahead and do it that way. Whoops. Two over 1 minus x squared. Well, x squared is like, again, let me write x. It's just like x minus 0 squared, right? So we're already centered at 0. So my r is x squared. My a is 2. And then we're rolling. And this is going to be converge whenever x squared is between negative 1 and 1. That's kind of a weird thing as far as negatives go. You can never get an x squared that's negative. So you can write it that way if you'd like. But that's the idea. All right. By the way, you can rewrite this as well as 2 times x to the 2n if you'd like, because of the power to power rule, right? You just multiply 2 times n. So there's, again, a number of ways to write this, but there you go. Now, if we didn't want to center this at 0, if we wanted to center this at, let's say, 7, well, then we'd have to use partial fractions in this. We'd have to factor the denominator. We'd end up with 2 fractions, and then we could center each of them individually at whatever we wanted to. Okay, in fact, you can do that on this example too. I'm not going to go through that, but you can rewrite f of x as a sum of 2 fractions, and then go for it from there. So center each one individually. Now, the other technique that you can use, or utilize, I should say, is one that comes up in this example. So let's say we want to find a geometric power series for the following function centered at 0. And our function is natural log of 1 plus x. Now, there's going to be no algebraic way to manipulate natural log of 1 plus x. And to manipulate it directly like we did in the previous problems, and get a over 1 minus r. There's no way I can rewrite natural log as a over 1 minus r. However, if I were to take the derivative of natural log of 1 plus x, I would get 1 over 1 plus x. So what you could do is you could say, well, earlier, way back in example 1, I believe it was example 1, I found a geometric power series for 1 over 1 plus x centered at 0. So I already know a geometric power series for this thing. So if I found the antiderivative of that, then that would be a geometric power series for the natural log of 1 plus x. Now, because I used a f of x as the natural log, I'm going to use a different letter, g of x, as this 1 over 1 plus x this time. We earlier saw that the way to do this centered at 0 is take 1 over 1 minus negative x. So we just get a is 1 and then negative x in there. And that worked whenever x was between negative 1 and 1. So whenever x is between negative 1 and 1, we're good to go. Now I know that my f of x, that natural log of 1 plus x, is the antiderivative of g. So when x is between negative 1 and 1, this g is this infinite power series. So what I can do is I can say, well, therefore, the f of x is going to be the power series I get when I take the antiderivative of this infinite sum. Again, this antiderivative is going to be with respect to x, obviously. So I can just take the antiderivative of this, and because of the properties of the antiderivative, that means f of x is going to be an infinite sum. Well, we're going to have to raise each exponent by 1, divide by the new exponent, 1 over n plus 1. And then I would divide by the derivative of the inside function, which is negative 1. So I'm going to put a negative there. All right. And then obviously you should do a plus c. You can figure out what that constant is actually in this situation, because remember, we know that f of x is really a representation of natural log of 1 plus x. So if you plug in, for instance, 0, all of this summation here goes away and you just end up with c. So if you plug in 0 for x, natural log of 1 is 0. So when you plug in 0, you know you have to get out of 0. If I plug in 0, all this stuff goes away, so I know c has to be 0. So you can figure out what that constant is. And therefore, this function here, this power series, is a representation of the function natural log of 1 plus x. So that's a clever algebraic trick as well, and that goes back to what we did in the last section, that section 9.8, when we talked about integrating and the radius of convergence staying the same, except for possibly the endpoints. So those are some algebraic tricks. Again, I'm not going to deal with a whole lot of algebraic tricks. Obviously, the ones that I'm going to give you on the test or something are going to look more like this: 2 over 2x plus 3, or 18 over x, or 1 over 9 minus x centered at various spots. I can center these things everywhere where the denominator is not 0. But you'll see in the book, they give you some other algebraic tricks too, like letting r be x squared, or using partial fractions, breaking this thing up into multiple fractions, or using integration or using a derivative to get what we are originally looking for. So there's a lot of different algebraic tricks you can use, but it all comes down to figuring out something that looks like a over 1 minus r and using that geometric series to deal with that. If you have time, you could do this one as well. I'm not going to do example 9 on my own, or excuse me, on this video, but if you have time, you can try example 9 on your own. -1 over 1 plus x quantity squared. Well, if you want to find a geometric power series for this function centered at 0, you just have to realize that this is the derivative of 1 plus 1 over x. So instead of integrating the power series that represents 1 over 1 plus x, you can take a derivative of the power series that represents 1 over 1 plus x. Okay, again, I'm not going to do that here, but if you have time, you can go ahead and try that. So that is it for this section, and we'll start 910 on the next video.